and also he has a master in geo-environment. So you will understand how much this topic is complex, because it's about structure and the interaction between soil. And that's the one reason why the Dr. Mahari is here. He's a chair because we need that expertise. And also we believe that that's the reason we can't see any prefabrication foundation in Australia. The reason, because getting that interaction, getting that behavior is quite difficult. It's not structural, it's not geotechnical, but it's a combination. Why it's complex, he will explain, because Australia has clay, expansive soil. So, so I'm going to give the chance to Bertrand to do the presentation. Thank you.
Good afternoon, everyone, and thank you for coming. First of all, I would like to thank our industry partner, the Australian Rainforest Company, and also the camp where I'm studying, participating right now, the Australian Research Council Center for the Advanced Manufacturing of Prefabricated Houses. So, good afternoon, everyone. And today, I will be presenting my research on developing an innovative prefabricated footing system for residential structures on reactive soil. So my presentation will start with an introduction on why we need to develop a prefabricated footing system, followed by the research aim and the specific objectives. The conceptual design will then be discussed, together with the research framework that will explain the planned experiments and numerical simulations. And then the summary will wrap up my presentation. The positive economic condition and increase in population here in Australia have led to a growing demand for residential structures. As you can see from this graph that I'm presenting right now, this is the graph that shows the cumulative market balance, the underlying demand, and the completions of houses. We can observe that the average completion of houses from the period 2001 up until the present is around 150,000 houses per year. However, the cumulative underlying demand increased to 220,000 houses, which means that we are not actually constructing enough houses for the Australian population. This means that we are experiencing housing shortage right now. And to make things worse, the strong demand for residential structures is being hampered by a modest skilled labor shortage. So the skilled labor availability is measured by the trades availability index. The trades availability index indicates an oversupply if the value we estimate is positive, and an undersupply if the value we estimated is negative. And it can be observed from the graph that in most major cities and regional areas, there is a modest undersupply of skilled labor. And this report is for the June 2017 and September 2017 report for the trades availability index. But I just checked the availability index for the July 2018 quarter, and it decreased from negative 0.27 to negative 0.38, which means that the shortage for skilled labor is getting worse. So prefabrication is a construction method where we construct off-site and then deliver the product and assemble it on-site. This promising method may alleviate our issues for the housing shortage and skilled labor shortage that we are experiencing right now. However, the significant advancements can only be seen for superstructures, but for substructures, we are still complacent and we still use the traditional cast in situ methodologies, which is actually labor intensive and weather dependent. So prefabrication of substructure will maximize the prefabrication industry to obtain faster construction and lesser or minimum manual skilled labor. To design a prefabricated footing system, we need to consider many things. This includes structural integrity, design for manufacturing and assembly, and one of the most important issues to design an ideal prefabricated footing system is considering the cyclic differential deformation of the footing system due to the reactive soils. So what are reactive soils? Reactive soils are the soils that can significantly change their volume depending on the soil moisture that they contain. So for example, if the soil moisture increases, the reactive soil will swell significantly. And if the soil moisture decreases, the soil will shrink significantly, which has a volume change, significant volume change. This can lead to center heave and edge heave, which causes significant damage ranging from minor repair to severe structural damages to not only to our substructures, but also affecting our superstructure. This kind of soil is actually 50% of the Australian soil. So you can see that most of the major cities are on reactive soils. And not only here in Australia, but also in other countries such as the US, especially Texas, and in the UK, in South America, and South Africa, they have this reactive soil. So this is not just actually in the Australian context, but worldwide. It's a worldwide phenomenon. Hence, the main aim of this study, of my study, is to investigate the performance of an optimized prefabricated raft footing system for residential structures on reactive soils. And the specific objectives is, first, the objective one is to develop an optimized prefabricated raft footing system based on Waffle raft, suitable for low-rise and lightweight residential structures on reactive soil. So our main goal is to develop a footing system that will conform to the stipulations based on the Australian standards. So we are going to consider the ultimate limit state and the serviceability limit state. So the ultimate limit state is the capacity of the structure, and the serviceability limit state is how your structure deflects based on the loadings and the soil structure interaction. The second objective is to investigate the performance of the developed system using field monitoring and non-destructive crack testing. So we're actually going to monitor a prototype of the system that we developed and check the performance using non-destructive crack testing. The third objective is to compare existing design methods for footing systems on reactive soils by conducting sensitivity analysis for each design process and establish a suitable approach to predict the behavior of the developed system. And the last objective is to develop a design guideline for the optimized prefabricated footing system through parametric simulation study. So this is very important because right now, we have guidelines and stipulations, standards based on the traditional or conventional fooding systems, but we don't have any available design guidelines for prefabricated ones. So this slide shows you the research framework. So I introduced the 4 objectives of my study, which is to develop an optimized prefabricated raft fooding system and so on. And to be able to obtain these 4 objectives, we have 7 steps. The first step is to initially conduct a literature review. The second step is to develop the conceptual design using a mathematical method. The third step is to conduct a field monitoring, which includes the non-destructive crack testing to check out the serviceability. The fifth step is to validate the developed model, the soil structure interaction model. The sixth step is to do the comparison, and the seventh step is to design the guideline for the prefabricated fooding system. So you can see that for each step, we're going to achieve the objectives. So for example, when we conduct the conceptual design step, we're going to achieve the objective 1 and so on. So this research framework actually acts like a map. So to develop the conceptual design, we use the topology optimization, which is a mathematical method that optimizes the material layout based on the design space within a design space based on a given boundary conditions and loadings and other types of constraints such as manufacturing constraints and so on. So for this example, you can see that this is our design space, and this is the boundary condition, which is a fixed boundary condition, and this is the applied load. So this is just a simple representation of the topology optimization. So this is the actual code that I used for MATLAB, and you can see that the material layout is being optimized, which is pretty cool, right? Yeah, so it will take some time and it's done. So the topology optimization, when you compare the traditional approach to the optimized approach, the traditional approach uses more material, which makes the product heavier, bulkier, and more expensive, while the optimized approach, it has less material, lighter, sustainable, and cheaper. And so these are the steps that we conducted. So we have the original design, which is based on the waffle raft. So you're familiar with different kinds of fooding system. So we use the waffle raft because first of all, it's economical, and second, it's practical, cheaper, and most Australian construction and design companies use it for residential structures, which will help us for the market uptake of the prefabricated housing, because it's this problem, this issue, it's not just related to structural, but also the commercialization, because people might not be ready to accept prefabricated fooding system because this type of system is novel. So we chose the waffle raft because it's practical and for the market uptake. But unfortunately, right now, I can't show you the conceptual design that we developed because of IP issues. But when it's ready in the market, we will let you know. But we use topology optimization, which is a very useful method. So the third step is the field monitoring, which includes the ground movement, footing movement, soil moisture. I forgot to add the matrix suction, which is very important to monitor. And we are planning to install this equipment in a site where we will have a control which is the waffle raft, the traditional footing system, and then compare it to our the developed prefabricated footing system. So we will install soil moisture probes and magnetic extensometers and linear variable differential transformers. So that's for the field monitoring. And to check out the effect of the ground movement and the effect of the ground movement to the structure, we will also conduct the non-destructive crack testing using tomography and I think another method which is related to pulse. So this is the model that we are trying to develop. Right now it's in the initial stage, but we just need to validate it. So the step 5 is to validate the soil structure interaction model. So when you say soil structure interaction model, it's the interaction of the soil, which is the reactive soil, and how it moves depending on, just like what I mentioned, soil moisture increase or soil moisture decrease, and then it will swell or shrink, and what's the effect on the footing system. So we need all the field monitoring data, the non-destructive crack data, the soil water characteristic curve, which is really important, and the shrink swell curve, which is based on the strain. So we need to validate that one, and after validating, we will have more confidence for the developed model, which means that we can do a parametric study and compare it to the other design methods, so we will know which one is the applicable way to use for a specific problem. So for now, since we have the model, I performed a preliminary simulation just to show you guys that depending on the used method, the required depth of your footing system or the dimension of your footing system will actually vary. So for this sample input parameters, which is from the literature, we performed a comparison comparing the Australian standards to 870, which is about the residential slab footing system design in Australia, the Walsh and Mitchell method. These are in Australia, and the BRAB Leeton, this is from the US. Holland WRA, which is the Wire Reinforcing Institute, the Post-Tensioning Institute, and other models. We compared it, and you can see that the maximum moment, the maximum shear, and maximum deflection actually varies depending on the method that you use. And it will give you a different required depth. So this is just a preliminary result. We're also going to perform more parametric study and sensitivity analysis for each method after we validate our model, our proposed model. So after validating and performing the comparison, we're going to conduct a parametric study to develop a design guideline for the prefabricated footing system. And this model is based on the total strain, which is affected by the change in strain based on the effective stress and the strain based on the moisture swelling. And we have the shrinking model and the swelling model. So just like what I mentioned a while ago, it's based on the change in soil moisture and soil suction, matrix suction. So in summary, we already developed a conceptual design for the innovative footing system based on a waffle raft using topology optimization, but unfortunately I cannot present it to you guys because it's a top secret. And we created a model for the interaction between reactive soil and the developed model by coupling the model of Wirasinghe and the concrete damage plus DCD model. So we just need to develop this model, to verify this model. And in summary, the research project has shown significant progress leading to some useful result, which is estimated to be approximately 35% of the total project. And the thesis is expected to be completed on time, which is around maybe January 2021, hopefully. So just to refresh you guys, the main aim of this study is to investigate the performance of an optimized prefabricated raft footing system for residential structures on reactive soils. And the take-home message of my presentation is prefabricated footing system for reactive soil is advantageous because it maximizes the prefabrication requirement, which is the construction period and the minimum labor requirement. However, gradual progress in prefabrication of structures, the study for this kind of structures, it's not that prominent yet. And and the second one is low-rise plus lightweight structures are more susceptible to cyclic ground movements because actually there's nothing to negate the soil pressure that the structure experiences. So especially for prefabricated houses, it's lightweight, so it's more prone to the movement, the cyclic ground movement of the soil due to reactive soils. And right now, there aren't many, there aren't many design guidelines for prefabricated footing system, which is actually part of my research study. So we need to develop the design guidelines. So I would like to take this moment to acknowledge Professor Priyan and Dr. Shanata for their guidance, and also Dr. David because he guided me for a year, and Dr. Madi for agreeing to be my chair, and Ms. Maral Tesser from the Australian Reinforcing Company, which is our partner, industry partner. So are there any questions?
What size you say residential, but that varies significantly. What size are you actually taking something?
So when we say residential structures, we're pertaining to the class 1 and 10A based on the building code, which includes 1-story to 2-story dwellings and garage.
How will your system handle surprise at the moment? I think at least 1 in 10 times when they're being footings, they find something that they haven't expected. What will happen to them?
I'm sorry.
I recently did some renovations and they got a footing surprise, so they had to modify the plan. How well will your system handle that? Because you've obviously designed it prior to that. So what will happen?
Yes, for renovations, I think it's kind of difficult to apply the prefabricated footing system for renovations. Like, when you say renovation, it's like, deconstructing and then building again. But maybe for extension, it's appropriate.
What I was actually thinking was when that happened and they found a problem, they said that happens quite often. So how well will your system handle when that surprise happens, when they have something they haven't detected in the soil? Current systems, they make workarounds. What will happen to them?
If
suddenly find a problem in the soil. That's not seen before. And again, Dr. Marty is expert here, but the soils, change and with time and droughts and also things and floods and rain.
If I can expand, that's a good question. So if you put the house on a stump and your design goes wrong, then you pay 15, 20, 25 grand and they bring jacks and they re-stump. The question is that if for any reason an unforeseen circumstance happens, you get a leakage, you get some gum trees and they impact. Does this system can manage maintenance? Because with waffle slabs we can inject underneath, we can do things. So let's say you design this, and regardless of your good design, for whatever reason you see movement, can you go back and then spend some minimal amount of money and bring back the system to where you want it, or no?
It's just to be fair on you, because this is for the new footings, but there's no reason once it's constructed, it's same like a conventional system, so same remedies can be done, right? So it's no difference to what is the underpinning or strengthening or anything that, but it could be even, so that's, I think that's a question which was asked.
Can I ask a question? Yeah, nice work. But I have a question about your field monitoring. So your field monitoring, have you got the site selected yet or not?
Not yet.
Okay. So, okay, when you design an AS2870, you design for a period of 50 years, yeah?
Yes.
And you definitely understand why we aim 50 years, yeah? Because the maximum expected movement to happen, we know that we need to go through certain climatic cycles. We need to capture extreme wet year and extreme dry. And the current climatic data suggests that we need 50 years. Now with climate change, that can happen more frequently. You can get maximum movement in 10 years. But we've been monitoring the site in Braybrook, and I have industrial partners monitoring the site in Horsham for 7 years. And what happens is that in 7 years you may not see movement, because this year we had a dry winter. Okay, so we didn't get enough rainfall. The site that we monitor in Braybrook, we have been monitoring for 18 months, and the potential of that site, according to AS2870, is 70 millimeter movement. On the ground, we have only observed 50 millimeter. And when you bring that 50 millimeter to a slab, you may see 1 millimeter, you may see 0, you may see 2, which would be in tolerance and in the accuracy of your LVDT system. So my question is that you're gonna imagine that, let's assume you have a site, let's assume it's a site with high reactivity, and let's assume you are in the site today, which you are not in. 99%, I can tell you, you're not gonna get enough movement in that site in a 2 years period. So how are you gonna use data then to validate your model? Because you started today and you keep monitoring the surface, you see plus minus 2, 3, 1 millimeter, and they would be within the accuracy range of the instrumentation, so you cannot rely on those results. So then what data you would use to, or you have alternatives to increase the movement?
Actually, we have an alternative method, because we also, prior to this, we also plan to do a laboratory testing, which is a small laboratory setup based on what Derek Chan from Monash and Virasing did. They conducted a laboratory setup for pipes. So we are actually planning to do a laboratory setup to concrete or a plastic maybe. So,
I think that's a very good question. Actually, we had that discussion. It's good you asked that question, because that's a good point. Like, if we can't validate using the big scale, then we are in a big trouble.
Yes.
So that's why that we came up with. But
it's a very good question, and I think we need to think about it. But there's no reason why we can't artificially create a reactive soil site. So, like have a site, dig it out and create a reactive. I think they have done those tests, as you know, as well. So I think very good question.
Other approach is that,
yeah, but we need some guidance
is
from
that
it.
you wait until close to the, you have a timeline. So you start monitoring, and then if you don't see enough data coming from the climate, so you don't get enough rain, then you flood the site, for example.
Flood the site, that's
so
true.
you bring it
Exactly.
back.
The artificial area, that's that's some advice you need to give as well. So there was one other question for the guy.
When you talk about prefabricated, how big are you talking about? What rafters including the size of a house area inside or?
So the average area for a house right now in Australia is around 240 square meters. And since the transportation of the panels are limited, we're actually planning to have panels like 2 meters by 6 meters, something like that. Yeah, so, and then just connected in the side.
How long do you think it's gonna take to mount that system in the site? Now, I do understand that's a commercial question, but ultimately you are doing this to reduce time and cost. So what would be the expected mounting and delivery time for such a system? So 1 day, half a day, 5 days?
Our target is 1 to 2 days.
Please, one last question, sorry, but we are running out of time, but
You said that the prefab panels will be about 2 by 6 meters. Is that limited just by transport, or is optimization and performance been taken into consideration with that area as well?
Right now, it's just by transporting.
Okay.
but you are welcome to stay and ask other questions. I think I'll conclude because it's, some others are having classes at 2:15, so thank you very much. Also just want to say that, thank you very much, Dr. Kasran Chani. We were in a, actually